Automation at IIC Bangalore. He's been in the news lately. I don't know. I'm just checking. He's been recognized for his outstanding contributions in HPC in India by as what Dr. Abdul Kalam HPC Awards. Is that right?
Yeah, APJ Abdul
And
Kalam Award.
yeah, and also in the news as Intel Rising Star faculty a few weeks ago, and he's very active in research, etc. Also, um, I think most of it. Arka, please feel free to share.
Sure,
Over to you.
sure. Yeah, thanks, Madhura. Okay, so today what I'm going to talk about is superscalar pipeline. Okay, so and I guess like in previous lectures by Professor Govindarajan, you have learned about pipelining, little bit about, I guess, out of order executions and things like that. And from there, we'll actually take it a little bit forward here in another aspect. That is what we'll talk about the superscalar pipelining, when we'll try to execute multiple instruction in each stage of pipeline at once. Okay. So that's the goal. But before we get into that, I want to have one slide about the three basic principles that you will see that repeated in multiple forms over these these courses. Not on this particular course, not only for computer architecture, but in generally computer systems. So whenever there is a performance optimization, it typically in one of the three axes that I'm actually pointing here. It will be either trying to take advantage of some kind of parallelism that is available. The other could be the locality, access locality. For example, caches is a good example for that. You try to take advantage of temporal and spatial locality. Yes, later in the this lecture series, you'll actually hear more about it. And of course, there is this speculation, right? Where you predict something like, say branch prediction, and if the prediction is correct, and then you gain performance, and if it is not, then typically you have to take some corrective action, right? So this is the three things, and superscalar pipelining is also an example of how we actually take advantage of parallelism. Okay, so with that in mind, let's jump into it. I guess you already have heard of this term called instruction level parallelism. So what we really mean by that, like at the end of the day, when the code is compiled and it is provided to the hardware, so what really software wants, and this is just assuming single-threaded software, is that you are provided a stream of instruction, and the hardware should execute them one after another. Kind of, it should give the illusion that it is getting executed sequentially, right? However, in that stream of instruction, there could be parallelism that is available because there can be instructions that are back to back in the stream of instruction that was given to the hardware, but they could be executed in parallel because they are independent of each other. So that's where the instruction level parallelism comes in. Basically, the number of instructions that are back to back but independent of each other, which means that in an ideal machine, if you had all the resources that you could wish for, then they could have executed in parallel. Okay, just an example. Look at this particular kind of pseudocode on the pseudocode or pseudo assembly, whatever you call, on the code 1 and the code snippet code 2. So here, how this terminologies mean is that here what we are trying to say is that we load on the register R1 the value of adding R2 plus another integer 1, right? Similarly, there is here R3 we are putting whatever the value was there in R1 and then divided by something, right? So what you will actually observe here that you know um, here this 3 instruction, the next instruction is dependent on the previous one, because unless you compute the value of R1, you cannot uh, start computing the value of R3. So there is essentially no instruction level parallelism, or in this case, we should say the ILP equals to 1, because you know what, no more than one instruction can be executed in parallel because they are not dependent. Sorry, they are dependent. On the code snippet 2, here you would actually see that each of these instructions are independent of each other, which means that ideally these all 3 instructions can be executed in parallel. So they have a ILP equals to 3. Now, as I say that ILP is a property of the program. I would actually say a little bit more carefully. It's not only the program but the compiler, because at the end of the day, it's the compiler also will ultimately spit out the binary that the hardware will actually execute. But it's you can think of it, it's whatever the hardware gets. On the other hand, how you can actually use this ILP to get the performance out of it. It depends on the hardware itself, right? And here how we quantify one of the key metrics to quantify the performance is instruction per cycle, or the inverse of it, which is the cycles per instruction. So if you are thinking about instruction per cycle, then higher is better, right? And if it is cycles per instruction, lower is better. So in terms of the relation between this ILP and IPC is that essentially instruction level parallelism determines the upper bound on the how much IPC you can actually get. Because if there is not parallelism in the program to start with, what can you do? What the hardware can actually do? Because if the instructions are all dependent back to back, then not much you can actually do about it to increase the IPC beyond, say, 1. And if there is more ILP, then it is incumbent on the hardware to be designed such that it can take advantage of it, and take advantage in the sense that it can provide better performance in terms of IPC. And superscalar pipelining is one way to take advantage of ILP that may exist in the program that is presented to it. So we'll start by understanding what the superscalar pipeline is with an example of the basic scalar pipeline. Okay, scalar pipeline is one where so let's take a look at this example or the picture that would be used. Okay, so first on the x-axis is just the time, and this is the stream of instruction that is coming, and these different colored boxes represents different stages of the pipeline. So here in this particular case, the example that we have taken, there are actually 6 stages in the pipeline. Okay, each of them are colored differently, and the depth of the pipeline is here D. The number is D. D equals to 6 in this particular picture, right? So what happens in the pipeline? That in the steady state, and if there is no pipeline hazards and so on, pipeline is all full. So then you will actually be able to get IPC of 1, IPC or the CPI of 1, both the same here. Because every cycle, one of the instruction will complete its execution. That's the ideal world. And this is the scalar pipeline. Okay, that's what we have read so far. Now, in case of superscalar pipeline, what really actually, what you have actually seen here is that only the overlaps happens between these different portions of these D instructions. Okay. Now, in case of superscalar pipeline, what you are trying to achieve, as I said, that if there is RLP available, we want more than one IPC. So what we will actually do here is that there can be multiple instruction in parallel, executing in parallel in each stage of the pipeline. Remember that in case of scalar or pipeline, that the baseline pipeline we will actually we were looking at there, in each stage of the pipeline there could be at most one instruction. Of course, if there are D is the pipeline depth, then there can be D instruction that can be in execution at different stages, but not at the same stage. In case of superscalar, we are saying that even within the same stage of the pipeline, there will be more than one instruction that could be executing. So how the picture would look like? Picture will look like this. So we are still sticking to the number of pipeline stages to D, but what we are now saying is that in each stage there can be n independent instruction. So what it means is that the amount of parallelism that you can actually have, where in an ideal, when the pipeline, this superscalar pipeline is completely used, then at any given point of time there could be D into n number of instructions that are in execution or in flight, right? So it's more parallelism. So that's what superscalar pipeline tries to achieve. Okay, and we'll see what are the challenges is present, or what are the things that needs to actually change, throughout this lecture. But this is the basic idea of superscalar pipeline. So as you can actually imagine, so with the baseline pipeline, there was maximum IPC you could actually get was 1. So here, if the superscalar width, which is this value n, which means that at each stage, how many instruction can be there in the pipeline in parallel, then in this case it would become IPC. Maximum IPC could be n, or CPI 1 by n, right? So that's what. So that's how you can actually try to push your achievable IPC beyond 1 with superscalar pipeline. So how it actually can actually look like? This is a very high level schematic diagram. How it actually look like? Okay, so as you know, initially there will be some fetch stage. There would be in a basic pipeline, right? And then you will have some kind of decoding, register read, instead of operand read. There will be some execution stage. There is a memory stage where caches and so on it would actually access and update. And of course, there is a write back stage, right? And here, what the color coding, the black and red, we're showing that effectively, you have one instruction in each stage, which is like in a black, and another one which is the red. Now, typically today, if you look at modern processors, most of them would be around 4-way superscalar, or it would be said in a 4-wide pipeline. These terms are interchangeably used. By that, it means is that so the n that we were actually seeing in the previous picture, that is typically n equals to 4 in modern architectures. Okay, so with that, we'll start digging more and more into what you would actually require to design such superscalar pipeline. Let's take an example. Okay, so the example, and we'll put side by side the first picture over here. Let me see if I have a laser. Yeah, this one we are showing that, okay, what happens when you have in a baseline scalar pipeline. Okay, these are the execution cycle count. These are these different stages in which an instruction is, and this is the instruction stream that you are asked to execute. And how how this instruction means, like LW, it is actually loading a word, and what it is actually doing is that its address is from where in the memory it should actually load, is in the register R1, and this is an offset 0 that it should actually add, get that address and put it whatever it is in that memory address to the register R2. Similarly, you can actually see these different, what this instruction would mean, and add. Here it's obvious that you'd add the content of this register R14 and R15 and put it on the R6. Similarly, this is another load. So now, if you look at this stream of instruction, you'd see that all this instruction, there is no kind of there is no need to just stall the pipeline. Okay, but you can actually see that there is an dependency here. Add, it is writing to no, sorry, there is no dependency here. Sorry, I think I got confused, R8 and R80. But anyway, just discard that. So there is, you can say these instructions are independent, and if you apply the two-way superscalar, this will fit in nicely, because now what would actually happen is this: these two instruction loads can now execute it in parallel, so they can enter the fetch stage, decode stage, execute memory, and all these things in parallel. So nicely you'll actually see that your execution will end early because of this two-way superscalar. Now, that's, we say that in the ideal situation, when there is no dependencies, that for which you need to actually put a bubble or stall in the pipeline. But let's next see, but that's not a realistic case, right? Like, often you would have to put stall or the bubble. So what really happens if you have dependence? So what will change is that what you would actually do is that change, earlier it was R14, this register, now we'll actually make it R4, so that this add instruction is dependent on this previous instruction. Now, what would actually happen in a typical pipeline is that there will be a stall here in the this decode stage, because what would happen is that until this particular instruction gets into the memory stage and the loaded value is ready, which means it can be bypassed to this next instruction. I am assuming that what the bypassing in the pipeline is. Then what would actually happen is that until this previous instruction, this load reaches the this one actually reaches the aim stage. This particular instruction, the next instruction, cannot get into this decode and the operand read phase. So it has to push a bubble here, right? Otherwise, you would get an older value in the R4, and that the execution will be wrong. So that's how it would actually work in a scalar pipeline. Now, what happens to these stalls when you are, talking about, say, this two-way superscalar pipeline? So here you would actually see, so these are all stall cycles. You could, first of all, what you would see here is that, the stalls would be more, and there is a reason for that. The reason is now, until, so, both these instructions, say load and add, they got into the fetch stage in the same cycle. However, this next instruction add, as we know, that would not be able to read its operand, which means that would not be able to get into the D stage until the previous instruction has gotten into the M stage, even with bypassing, right? Even if you can actually bypass from M stage to the D stage, operand read, even with that, you have to wait until this Since they started in the fetch in the same cycle, unlike here where the add started one cycle later, here you have to push two bubbles. And as soon as you do that, here what would happen is that this one actually starts later, and this is a in-order pipeline. So you have to actually put stalls here too. And here there is one more dependency that we actually created. Here also there is one more stall you need to actually add, because there is a dependence between R8 and R8 here. So this, unless this add instruction get into the execute stage, this particular load instruction cannot get into the DR operand read stage. So what it means is that you have to actually put extra bubble or stall here. Now you can actually see that the same dependence is here too in this code, so R8, but there is no stall here, right? The reason is that you could actually bypass. Here, the value would actually become ready in the execute stage. And if you can actually have a pipeline has the bypassing, so you don't have to wait till the end, write to the register to get the computed value of the previous instruction. So you can continue without any bubble. But here, since you actually started the fetch of these two instructions in the same cycle, this needs to wait at least the previous instruction reaches the execute stage. Otherwise, the value of R8 is not ready, which is necessary for this load to continue. So the basic point here is that with the Superscalar pipeline, as you can see, that as an idea, it is pretty simple, that you are trying to execute more, have more and more instruction in the same pipeline stage for parallelism. But in a real world, when there are dependencies among the instructions, there will be more and more bubbles. And how how many instruction you can actually pack in each cycle to each stage is of course is not always 100% in terms of like if you have a 2-way or 4-way, it would not always be that all of these instruction can be in the pipeline in each stage at the same time. So with that, one of the things that we want to I want to quickly mention is this. There's this so Intel Pentium was one of the first processor that came with the Superscalar pipeline, and they had what they call the pairing rules. What are the instructions that can go in parallel, and what are the type of instruction that should not go in parallel. So a few of them, some of the rules here. So that's called the Intel Pentium pairing rules. First of all, here what is actually happening is that it is moving a particular integer value in this instruction. So is to a EAX register, and then it is putting this value in the that is actually there in the EAX in the memory that is pointed to by the EBP. This EBP register is counting the address in the memory where it wants to put this particular value that is there in the EAX register. So you can see there is a dependence here because unless this kind of instruction gets completes, this next one cannot actually execute. So they would not pair them together to go in the pipeline at the same cycle, because they will get stuck. You have to put stalls. There is this second rule is about output dependence. Here, what is happening is that you are writing to the same register EAX. So that means that you have a chance of overriding each other. So that's also a type of instruction. They would not, pairs of instructions that they would not allow you to push together in the pipeline. There are these instructions in x86 ISA where you have a register which has actually a lower half and a higher half, like two portions. And if there are two instructions back to back that are writing to the same registers but like in different parts of the same register, then that also is disallowed. And then there is this other constants that you typically have based on the how many functional unit you would have. Like it's not only the dependence, but let us assume that you have say, just for an example, you have say 4 wide superscalar, but you just have say 2 ALUs. Now, what would actually happen is that even if you try to execute them in parallel, you will essentially have like structural hazard, right? Like you won't have that in execution unit to compute, right? That because you don't have enough ALUs. So there are rules on based on how much functional units that you have provision for, and if there are back-to-back instructions that uses like takes long on the execution, then they would not be scheduled together either. So this is an example of and kind of a pairing rules that Intel Pentium came up with, which was one of the earlier superscalar processors. So a little bit. So what we'll actually do from now on is that we'll get into in understanding and complexity of take an example of a 2-issue pipeline, and we'll try to understand the complexity of how to of designing and superscalar pipeline. Okay. So so first stage, of course, is the fetch. Now remember that in a fetch of an instructions like data, there will be like catch blocks that would contain the instruction that you will actually have to execute, and a single cache block would actually have multiple instructions in them. So if there is no branches and the instructions that you are executing, they are within the same cache block, then that is all good, because anyway you have to actually bring in the cache block to execute. Say the first instruction, the second instruction is also there in the same cache block, so that doesn't make the fetch much complicated. Also about branch, because branch actually changes the program counter, what is the next instruction that you have to fetch and execute. So that is impacted by the branches, because as I said, it changes the program counter, which means that it impacted by the branch prediction as well. And we'll see a little in bit later, in a bit, that how branch prediction and branch prediction accuracy can affect superscalar pipelining. But for now, typically, without creating too much of complexity, you might have ability to predict one branch per cycle. So then, you have to also, be careful about checking the conflicting instruction, and say, and we are talking about like the instruction that can execute in parallel, but if they have dependencies across within the registers, they might have to introduce stalls as well. So this is something that the decode stage have to be aware of and be take care of, because in the decode stage here we are assuming that the register read would happen as well. Okay, so the question is that if you try to do all of these, so what are the kind of hardware costs that gets added, right? The first thing is that remember, now we can actually see that so many lines out of the register file. Okay, you can actually see that there are 2 lines that are coming out of register file to this decode or register operand stage for each of this color, which means that each of the color represent one instruction, and there are 2 of them coming. The reason is typically here the assumption is that your instruction set architecture is such that in each instruction, you can have two source register, and you have to read both of them to execute, right? And so if it is a two-way, so then you can actually see that in a given cycle, and if it is a two-way superscalar, and by the ISA there can be two instructions, two source registers that can be read, then at at a given cycle, to decode such a two-way superscalar processor, you would require to read out 4 registers values out of the register file, right? And you can also see that since there are two instructions that can be at the write back stage at the same time, you can have a need to write 2 register value at the same time in a given cycle to the register file. So now to support all of these, you need to able to support this parallelism in your register file too. So typically, what would people do is that you'd add more ports to the register files. Yeah, there is a question. Is there a question? I hear somebody. If you are not asking a question, please mute. Hello? Okay, fine. Somebody is still not muted. Students, please mute if you're not asking a question. By the way, I can't see, since I'm on a full screen mode, I can't actually see the questions that you might actually put on the chat. So at either one of you have to actually interrupt me and say there is a question, read it out, or if you have a question that you need clarification immediately, you can unmute yourself, ask the question, and then go back to mute. So maybe do any of you want to ask a question? Have a question? This is a good time.
Sir, I have a little off question, sir. So suppose, is it possible for me to execute two processes in using this two-way scalar?
Two processors.
Processes, like two processes, like instead of having a context switch within them, I want to execute
two processes. Okay.
Yes, sir.
Okay, so we would not get into this right now. We are just assuming that there is a single stream of instruction, which means that a single thread of instruction actually coming in. Okay, so that is what you assume, not more than that. Okay, so I don't know whether we'll follow, do probably multi-threading in a simultaneous SIMT and so on, single. So then I think at the SMT, sorry, so simultaneous multi-threading. So then these questions might actually get answered better. For now, we have not gotten into multi-threading. So just assume that this is a single stream of instruction that is actually coming in from one of the processes. It's a good question, but you
Yes,
probably won't have the context right now. Hold that question for later.
Sir,
okay. Any other question? Yeah, go ahead.
So multi-threading, it will be a GPU, no? It will not be a superscalar. In that case, it will become a GPU content.
No. There can be no. There are you do actually hardware multi-threading within the CPU cores as well. Multi-threading doesn't necessarily mean that it would be a GPU. I guess it would be actually taught in the later part of this course. There is, for example, when you buy and say Intel processors today, they will sell it, oh, Intel i7, this, that, and so on. Okay, 4-core, 8 threads. What is this basically? These are not 8. They are not talking about software threads. They are talking about hardware threads. So which means that there are actually 2 threads per core. This is called, they call it hyper-threading, or other terminology, academic terminology is simultaneous multi-threading. I would not get into this. We'll get derailed. But again, we have not started talking about multi-threading and so on, parallelism. So hold on to your question till then. Any other question related to whatever we have seen so far?
Sir, can you move 2 slides back?
Yes.
The second case. Sir, for example, when I'm comparing the 4th stage, right? So before decode, in the 4th instruction, add R4, R5, R6.
This
okay.
one, right?
No, in the two-way superscalar one.
Okay, so let me actually open my laser. Yeah, this one.
Yeah.
This guy.
So in this particular case, it would go at decode stage first, right? In decode stage, it would know there is a hazard. So why is it stalled at fetch stage?
Yeah. So it is actually stalling at decode stage only. It is unable to execute, move forward from the decode stage. So it has done fetch, right? After that, it is stuck there. That's why you are seeing this D starts.
No, what I essentially mean is that during decode, we do the register reading, and at decode, we know it's a hazard. So what I essentially meant to say is that the next 2 instructions, which is the next 2 add instructions, they can be fetched simultaneously, right?
Oh, which one? This one, right?
Yeah,
R4.
this one. Yeah, this one would be stuck at decode stage. So the next 2 can be fetched.
Oh, we are actually assuming in order pipeline here. So unless these instructions actually move forward, the next instructions are not being brought in. So I guess this is clear, right? Why this instruction should stall, or put bubbles. This instruction should stall, and then next, as this moves, you actually put in 2 instructions in the fetch stage.
What I essentially meant was that it would fetch in decode stage and not. Okay, I'll just ask in the doubt session that will happen. I think I'm getting confused at one point or something. Yeah, thank you.
Sure. Oh, sure. Fine.
So I have a question.
Yeah. Right.
So regarding that only, the program you showed just now. Superscalar part.
Yeah, this one.
So I have a doubt in the last instruction. So in the last instruction, it is decoding when the second last instruction is yet to be executed. So I think first the second last instruction has to be executed. Only after that the last instruction can decode, isn't it? Because it needs the data from the second last one. So there is data dependency.
Yeah, but there is a bypassing. You have talked about the bypassing, like pipeline bypassing of the.
Yeah, we had.
Yeah.
But
So
how it is happening here?
So what would actually happen is that you would actually read once this execute is at the edge, there is also this edge where you actually read out of the clock edge, that you would actually read the register. So there is the clock as a upper edge and falling edge, going up edge and going down edge. So you can actually read that. So the previous instruction who will actually feed you your one of the operands, which is here R8, right? And that would be the output of the previous instruction that is getting executed from the ALU. So it would not go via the register file, but will come out of the ALU for this next instruction. So instead of reading it out of the register file, which is the R, otherwise it has to read it from the R8, it will get it out of the ALU's output. So that's the bypassing.
Oh, so you are saying in the in a single clock cycle, in the first edge it will execute and in the next edge it will decode. something like that.
Yes. So basically, this is the register file read. So that is why it would that's how we actually get the operands, not necessarily register file read. So what it would actually happen is that so in this penultimate instruction, right? This guy. Okay. So penultimate register, what would actually really happen is that its value would be computed, right? ALU would actually compute the value would be ready, and in a normal case without bypassing and so on, what would actually happen is that it will go to the register write state. It would ultimately, of course, be there in the R8, and then the later instruction, the last instruction, will read it out of the register, the R8 from the register file. So with the bypassing, what can actually happen is that instead of that, you directly feed the value from the previous instruction, which is actually computing, directly to the next one, which is actually depending on that. Because you would not require, so when this value of R8 would be required, it would be required in this execute stage onwards, like essentially from execute and memory stage for this one. By that time, the R8 value by add is already computed because it is ready in the cycle 7. Does it make sense? What you were supposed to do is that in this decode read register stage is that get it from the register file. You did not get it from the register file. Instead, you actually got it there and pushed it in your execute and memory stage onward.
Yes, sir. Understand.
Okay. So this is the case of pipeline bypassing of in pipeline, because this is also otherwise you would actually require more and more stalls. So I'm assuming that you know about bypassing in the pipeline. You know, right? Like it has been taught. Is that right?
Yes, sir, it was taught just now, but because too many things were taught, so it got mixed up.
Yeah. That's okay. That's okay. Good that you actually asked the question. Any other question?
No, sir.
Sir, after
By the way, you can watch on. So what is the? We have half an hour. Okay. Yeah. Ask quick question. Yeah.
So after decoding the instruction, then only we'll know that we should insert a bubble or not, right? So, but in that add or even the load case, you are adding the bubble after fetch only.
No. What is happening? Fetch after means that particular decode. Think of it that it could not actually complete. It is stuck there. So this D starts means that it is stuck in the decode. Because the previous one, you now see that, oh, I was actually depending on this this previous instruction, can't move ahead, can't move this instruction to the execute stage. It can only complete the its decode and whatever register read that it has to do only in the cycle 5 in this case. It tried to get into the decode stage. It is actually stuck in that decode stage. And then in the cycle 5, it could complete its work that it should have completed as part of completing the decode stage for that instruction. Decode stage does include here the register operand read as well. Does this make sense? That's why you are seeing this D starts.
Yes, sir.
Okay. Any other question? Okay, good. So we'll move forward. Let's see where we were. We talked about this. Okay, I think this is where we were. Okay, so we talked about, I think, multiporting.
Hi, Arka. There are some questions in the chat box also. Did you get a chance to look at them?
I think I answered whoever asked the question. I think we'll move forward a little bit.
Okay. Then towards the end.
Yeah, because
Running out of time. Okay.
Yeah.
Sounds good. Sounds good.
Yeah, we handled at least 5-6 questions right now.
Sure.
So
Sure.
we'll
Okay,
handle
that's fine.
it better. Okay.
Okay. Anyway, we'll have doubt clearing sessions, so they can post it that time also.
Yeah. Okay, fine.
Thank you.
Okay. So, okay, we talked about the multiporting of the register file, and So, and the easier part is that adding more and more execution unit, because at the end of the day, if you're trying to add 2 instructions in the same cycle, both of them could be in the execution stage, then you have to have resources to compute, right? So that part is easy. The harder part that we will be talking about, it is bypass paths. We talked about in a, someone was just talking about this bypass you just learned, and now this will actually get more complicated when we are talking about superscalar. We'll see how. Okay, and memory unit, and we have seen that there are this how the stall cycles can get actually introduced because of if there is a load, and one stall cycle is probably fine if you are actually dual issue, but if you are actually multi-issue, you have say 4 issue and so on, you might also want to have a larger or many number of ports to the caches as well, so that you can actually get access the cache caches, multiple of them, like you can have parallel access to the caches as well. So this will also add to larger area, power, and so on to the caches as well. So what we are getting at here is that what it means is that for having in superscalar pipeline is that there is a lot of cost, hardware cost, because many of these portions of the processor that needs to now support parallelism. Okay. Okay. So the the few other things that comes up as the superscalar challenges of implementing superscalar processors, looking at the front end of the pipeline. So typically in a pipeline, the front end stages are these stages that are before the execution stage, which means like this fetch, decode, and so on, right? Register, read, and so on. So what really happens is that you need to be able to fetch multiple instructions at the same time. Typically we have talked about like if the instructions are in the same cache line, so you don't have to worry about getting multiple cache lines, but you might have to actually read out of the instruction cache in parallel. Of course, you would require more decoders, because you have to actually decode multiple instructions at the same time. Then you will have like what's called the wide instruction issue, and this is where complexity starts, because you have to figure out the stall logic. Now you have to consider that there are these multiple parallel instructions that can be in parallel, and typically, as we'll see, that if the superscalar width is n, the complexity grows at a quadratic of that. And we have also already talked about how the register read needs to be actually register file needs to support multiple parallel accesses, which means that multiple ports, like 4-wide superscalar, if you have 2 register operands, then you would require 8 read ports. Okay. So in terms of the challenges in the back end of the pipeline, is the execution stage, memory stage, write back stage. These are you have to have wider instruction execution, which means that more and more ALUs and so on. You have to have wide register write back, because multiple instruction can finish and be in the write back stage at the same time. All of them might want to actually write to the register at the same time. The big problem or big challenge is this wide bypass paths that will be taking a look into depth. It grows in the order of quadratic of the number of the width of the superscalar. which means the number of instructions that can be in parallel in a given stage, multiplied by the number of stages of the pipeline that can produce a result, because the bypass can happen from any of those stages. Okay, so this is a big cost of implementing superscalar processor. And another fundamental challenge is that you can build all this hardware, but ultimately, if you are presented with a code that has all the instruction back to back are dependent instruction, which means that ILP equals to 1, you can have all this fancy hardware, but there will be no use. Your IPC will be back to 1 or below 1. So defeating the whole purpose of having superscalar. And this is why compiler can help too, because compiler, if it is aware of this superscalar processing, it can try to arrange instructions that are back to back, are more independent. Okay, so now we'll get into each of these challenges into a little bit more depth now. So what we're actually trying to do is that give you high level views and then get into depth of each of them a little bit more. Okay, so we have to move forward quickly. So what it really means by having superscalar decode and register read, what really is involved. So in case of actual decoding, if the instructions are actually fixed length, then parallel decoding is not a hard thing. You just have to have multiple decoders. The reason, but if it becomes harder, if it is actually variable length, instruction sizes are of variable length, because if it is a fixed length, then where each of the instructions actually starts, the addresses it starts. The first, say, nth instruction and n+1, where they actually start. So you can actually start decoding them in parallel. But if it is variable length, then until you decode the instruction, the nth instruction, you don't know where the n+1 instruction starts, because the nth instruction can be 2 byte long, 4 byte long, 8 byte long. So it becomes harder. So this is a challenge that comes up when you are, it depends on the ISA. For example, x86 ISA is a variable length, ISA, while ARM ISA, it is, more, fixed length. So decoding becomes actually harder for x86, particularly in the context of superscalar. So they play a lot of tricks for that, something called a microcode optimization. Not get into the details, but if somebody wants to know more about it, search for micro-op caches, micro-ops in x86, what they are. It's called micro-op operation. So then about register files, we have talked about it. Just adds more complexity to the register file, because you have to have more ports and parallelism. The problem becomes more interesting part that we talked about. This the stall logic becomes a big issue, because it becomes order of n square. So how? First, think of the stall logic in case of an scalar pipeline. Okay, so what we are actually talking about here is that in the previous instruction, which is in the, say, M stage, if that operand is actually a load, and then what you have to actually check here is that the RS1 and RS2, these are source operand register 1 and 2. Okay, and this is in the, say, register read or execute stage. Okay, whichever instruction is in this stage, its source register RS1 and RS2, you have to check whether they are the same with the instruction which is in the, say, M stage or execute stage. Its destination register. RD is the destination register. So think of the instructions that they could read 2 source and produce 1 register value, right? And if this matches, basically you are comparing 2 comparison, then you have to actually stall, because the previous instructions output would become available only at the end of the M stage, and you cannot proceed to the execute stage for the next instruction until it actually completes that stage. So you have to put one bubble there so that you when the next instruction gets into the execute state, it gets the right results. Now, if it was a two-way superscalar, the equation would suddenly get much more complicated. The reason is now there can be two instructions which can be in the M stage, right? And there is two instructions which can be in this read operand stage. So for each of this combination, now there is 2 into 2. For each of this combination, you need to check if there is any match between the previous say two instructions which are in the M stage, their read operand, their destination operand, sorry, RD, with any of the source operand of the instruction that are actually following. And if the width here is 2-way, which means that two such instruction can be in parallel, which means what happens is the number of comparison, as you can actually see, suddenly becomes order of n square, where n is the width of the superscalar width. And of course, the actual term is 2 to n square, but that is order of n square. Not only that, you have to make sure that the instructions that are actually trying to execute in parallel, in the same, within the same cycle, there is no dependence between them as well in terms of previous instructions destination registers and the next instructions source registers. So what you can actually see is that in the pipeline, you have to actually put the stalls, and the stall logic, which means that it determines where you are putting these bubbles, becomes significantly more complicated. In terms of executions, as we have actually talked about, this is relatively easier problem. You can replicate your say ALUs, your multiplier, divider, and so on. But it's not that you go ahead and replicate all types of ALU instruction, ALUs, divide, say you'd probably have for floating point divider and so on. There will be a generic ALUs as well. You don't actually replicate all of them, multiply all of them by the width of the superscalar, because that will be actually too much. You don't need it, because not in every cycle you won't actually have two ALU instructions and so on. So this is more of an empirical analysis, and you will have some mix so that you don't get into the structural hazard often in terms of adding more and more execution units. We have talked about so how the caches may need to actually become multiported, because you have to actually access multiple of them in parallel. However, also here notice that not all instructions are memory instruction like load stores. Typically, empirical rule of thumb is that around 20 to 25, actually I would say 30 up to 30%, 1/3 of the instruction can be load stores in a typical program. And out of that, maybe another one, maybe you can think of like 10% of the instruction overall could be stores. So if you do these empirical calculations, then typically the designers come to a conclusion. Okay, how many number of ports we can actually add, so that it would, on a typical program, it would not create a lot of structural hazard, because you don't want to add resources assuming the worst case behavior, where if say every instruction is load or store, because that is wastage of resources. Okay. And we have talked about this, that if you want to actually increase the bandwidth, you typically do multiporting. You can also replicate, but this is something that is not done. Replicate the same cache twice, but this is not typically done in today's processors. What you do is multiporting, where you can access the caches, same cache at the in the same cycle to read multiple addresses, multiple registers out of it. Okay, so next is, this is the interesting part. we talked about how the bypass gets complicated. So now before we get into the bypass of the, what really happens in a bypass, right? So instead of in general, as you look in the instructions, you should actually read your operands out of the register file, right? So that's how you typically the instructions should execute. But the register write happens at the write back stage, which is the last stage. Sometimes the value that you're looking for and you actually write to the register is already available before that. Like, for example, if it is the add instruction, it is available in the execute state. So the point is that why do you want to wait till the write back stage and then read the value out of the register again for the next instruction? So that's wastage of time, right? This is where the bypass optimization comes in, where it has to actually take a decision whether it should actually read the register value that it's reading out of the register file or from the previous instruction. In case of an scalar pipeline, what actually happens is that the stage that you can actually say feed your instruction from value from is the previous instruction, right? In case of in case of in a superscalar processor with say n in a superscalar width, there can be n options, right? And not only that, for each of these n instruction that can be in the pipeline in a given stage, each of them would require can get it from any other instruction in the previous cycle, right? That was getting actually any of the n previous instruction that could be before it in the program order or in the binary that is presented, the instruction stream that is actually coming. So what really happens is that it could be either the input can be actually should be read from the register or any of the n previous instructions. And this is true for each of the n instructions that are currently getting into this this register read phase, that it is there in this register read phase. So what it means is that the amount of options, the bypass network, as we actually talk about, that here it is actually trying to get, this is the register decode, this is the register read phase where it can actually get the instruction, output out of any of these the instruction that are in the n instruction that are already in the next phase. Okay. So overall, what happens is that now it becomes the bypass network becomes n squared, order of n squared. Not only this, what we are assuming here is that only one stage in the pipeline could produce a result, which is say execute state, but that's not always true, right? It could be in say M stage for a load instruction. Sometimes if you have a deeper and deeper pipeline, what would really happen is that there are more than there is execute stage 1, execute stage 2, depending on, and there is memory stage 1, memory stage 2, and so on. So there's a deeper pipeline, and there are more and more stages of the pipeline for which, during which the result of an instruction can become ready. And it can be as say P stages, right? And what it means is that in that case, the bypass network has to be an order of n squared into P. That's the order would be, because for any of these previous instruction from which you can bypass the result without actually getting it through the register, as soon as they get ready, you catch the results. So that the next instruction can immediately start. But the question now would be that for each of these n previous one, there is p different possibilities when the result can become ready, which means the complexity grows to order of n squared into p. So in general, the point that I'm actually trying to drive here is that when you look at this superscalar pipeline, we do this so that you can take advantage of instruction level parallelism that can be there in the program. As idea wise, it is very simple. You say that in general pipeline, you can have one instruction to be executing at any given stage at any given point of time. Here we're saying that at any stage there can be up to n different instructions that can be executing in parallel, all good, but it suddenly complicates a lot of things like bypass network, like stall logic. This starts growing with the order of quadratic of the width of the superscalar pipeline. So these are the costs, right? I would actually, how much time we have? This is not so important. Yeah, this is, I'll actually keep more time for discussion later. I think I have a branch prediction discussion as well. Yeah, so superscalar fetch, I think we have already talked about. Now this is not so problematic as long as the instructions that you are actually trying to execute in parallel are within the same cache block. And if it is not in the same cache block, sometimes you might want to access two cache block, instruction cache block. By the way, these are in parallel, A and A1. But in that case, you would actually require banking or some multiporting of your instruction cache. Okay. Yeah. So the other thing that we want to actually discuss is whenever we are discussing about fetch, this question is always there: what instruction to fetch next? If you don't have branches, then the answer is very simple. The next instruction, right? Like PC plus 1. So life is easier. But programs do contain branches. Okay. So what actually happens? But it's not that okay, all the instructions are branches. If the branch is not taken, which means that you don't jump, then also basically what happens is that it is like an effect is like that. Okay, you didn't have the branch, so you are following the straight line of code, right? But if you have branches, then what you have to jump, and the straight line of fetching of instruction one after another doesn't work. So you have to actually put some, either you actually flush those instructions out, as you have talked about in probably in the branch predictions and so on, when if we take things actually go wrong, and basically or you stall till the branch is resolved, or the answer of the branch. This is where also compiler can help, because it can do things like loop unloading, because remember that there is always a branch at the end of the loop body, and it can actually unroll. Compiler can unroll the loop multiple times, especially if it knows how many times that loop will execute. That would reduce branches, and that makes life of a superscalar processor and fetching easier. Other things that I want to quickly cover, we're running out of time. Branch prediction actually has an impact, actually more impact on superscalar processor. So let's see why. So let's take this example. Let us assume, remember that for an n-way superscalar processor, the ideal CPI or cycles per instruction is 1 by n. So if it is, this is cycles per instruction. So if it is a 4-way, then it is 0.25 instructions, 0.25 cycles that you should actually take, on average to execute an instruction. In ideal case, that's the best that you can actually achieve. but of course there are stalls and so on you have to introduce, so it will be less, more than that. So now let's see what actually impacts this more, why we say that the effect on superscalar performance is more for branch prediction. Let's take this example. So let's assume that so 20% of the branches, 20% of the instructions are branches, and 75% of them are actually taken branches. What is the taken branches? Which is like where you have to jump. Remember that if it is not taken, you can actually flow through that PC plus one kind of thing. And let us assume that there is you take 2 cycles to figure out, resolve the branch. And if you do not have, say, any branch prediction, which means that it is equivalent to having wrong prediction all the time, because you have to wait for that 2 cycle for the branch to actually resolve. Then if it was actually scalar pipeline, so then you know that the ideal IPC that you can actually achieve, sorry, not IPC, CPI you can achieve is 1. And then if you take this 2 cycle penalty and there is 20% branches and 75% is taken, then you would actually see that this extra overhead that it would add, and if you do the math, it would become 1.3. So because of these branches, there will be a 30% slowdown. Now, if it is a two-way superscalar, so then your ideal IPC CPI would be 0.5, but this factor doesn't change because there is still 20% branches, nothing we can actually do about that. 75% of are actually taken, and it takes 2 cycles. So if you do the math, you will actually see that now the slowdown in a relative term would be actually more. So the basic thing that I'm actually trying to drive here is this, is that if you go after highly superscalar processor, like if you have a superscalar width which is actually larger, then you should also not make this, be aware of this complicated bypass and more complicated the stall logic. You have more porting in the caches, but also you need a better branch predictor, because the relative cost of branch misprediction would be more and more as you go for higher superscalar width. So these, it's not that you can actually make the pipeline superscalar but don't improve the other parts of the pipeline. Ultimately, they will take away most of the benefits that you could have, you might have thought that you can actually get out of superscalar, processing or superscalar pipeline. So that is one of the important message that I want to convey. So the other thing is that this is slightly, I'd say tangentially related, but this is something that I wanted to mention because we do have this concept that often that, okay, pipeline means that there are 5 stages, they are all equal and so on. All equal in the sense is that, okay, 5 or 6 stages, some number of stages. But in a real pipeline, what happens is that, it is understood pretty well that different instructions require different amounts of time and complexity. Our add instruction, an integer add instruction, is much simpler and takes much less time compared to, say, a floating point division operation or multiplication operations. So typically what you would actually have is that the front of the pipeline, front end of the pipeline, this is the fetch, decode, read register, this will be same. These are some of the things that you have to do anyway, irrespective of what kind of instruction it is. But the execution part is different. So that's why one of the things that you actually, what happens is that execute stage is the branch, floating point have my part of the pipeline might be deeper than the ALU part. Okay, so this is something to keep in mind, because you should not always think the pipeline as, okay, one thing that is unified for any type of instruction. So this is, one way to picturize this, other way to picturize is that you also remember in a real hardware, what really happens is that you typically would also have like integer register file, some floating point register file, and this is say the floating point pipeline, and this is the say integer part of the pipeline and so on. Typically the floating point pipeline portion of the pipeline actually after, again, like the first few stages will be same. After from the execution stage, different based on the different types of the instruction, they will get to different pipeline execution stages, and they can look different with a different depth. So this all actually adds to the complications, especially when you are actually talking about superscalar processing. I'll end by saying what is the trend of today. So as we talked about, right, like, the Pentium was one of the first processor, that commercial processor that actually introduced superscalar processing. But even if you look at today's processor, you would not see more than 4 issue with. They are not trying to actually push more than 4 instructions. So that's not much of a jump, right? Going from, okay, basic superscalar is 1, it's like, base scalar pipeline, and then you have gone up to only 4. That's today's situation. Even if you took, and this is Ryzen 2, even if the Ryzen 3, this is even today's absolute cutting edge, you would actually have 4 superscalar. The question is why? Can you actually mute if somebody has actually unmuted themselves? Okay, so the reason is that why people have not actually increased. So few of the answers you already have. That it adds cost. We have talked about how the superscalar, bypass and everything actually blows up. You have to have a branch prediction accuracy and so on, high and so on. But there is also an characteristic of the applications that also limits that how much width you want. There are studies that actually shows that typically it's about 5 instruction, every 5 instruction. These are all rule of thumb. These are all empirical analysis. But typically after every 5 instruction, you will hit a branch instruction. And the problem with the branch instruction is that you don't know. Of course, you can predict and so on, but basic problem is you don't know what next, right? Which instruction to fetch next and execute next, and it's limit not only branch. There is also this other thing that there is this data dependency as well, where there are some studies that if you typically on an average an instruction that is actually producing some output and some other instruction that is actually consuming, they are not too far away the way that people write programs. So if the amount of instruction level parallelism in typical program is typically limited to, I think, 4 or 5. Yeah, typically average 5. So if you go anything beyond issue with of 5, most of the time you would not have enough ILP to keep these 4 stages busy. So it doesn't get you any benefit. And this is where compilers again can help by deciding how they actually can spit out more optimized code as they create the pipeline. So that is something like to learn about, know about. I think later in the classes there will be a discussion about the BLUE, that is a compiler-driven approach. So you learn about how to actually compiler can help to pack instructions that are not dependent on each other. So with that, I'll stop here. So if there is any question now, I can take a couple of them now, and maybe later during the doubt clearing session. Any question? Okay. Yeah. Go ahead. Okay, I guess no other question. So I guess now there is a break, right?
Yes.
Oh,
Thank you, Professor Arka, for the detailed
sure.
lecture. The next lecture we'll have at uh, 2:30 by Dr. Ashish Wilkar on VLIW architectures, and after that we'll have a doubt clearing session. So please note down your doubts so we can have a discussion on that. Thank you once again, all of you. We'll break now.